Hello, in this lecture we will find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD of this rectangle equals to 3 units in its length. In addition, inside this rectangle we have those two semicircles. The radius of this big semicircle is 2. The radius of this small semicircle is 1. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles, they are all right angles. So this is a right angle. This is also a right angle. This is a right angle. Finally, this is also a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle. This point is point P. We will define the center of this small semicircle. This point is point Q. We will define the touching point of those two semicircles with each other. This point as point S. Likewise, we will define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we will define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction. That is to say, we will extend line segment AE inside DC of this rectangle by a straight line until they touch each other. This is their touching point, so we will define this touching point as point F. Socially, we know that side DC of rectangle ABCD, it is absolutely a straight line. Then, by doing the construction, we extended the straight line DC by straight line, and the result is DF. When we extend a straight line by straight line, the result must be a straight line. Therefore, DF must be a straight line. If you focus on the upper side of this straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So here we have the small right angle, triangle ECF. We will define this angle EFC, as alpha. We will continue to focus on the small right triangle, triangle ECF. this small right triangle is CF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle in DF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in any triangle is equals to 180 degrees. Okay, so here we have PD equals to PS. Both those two line segments are the eye of this, or the radii of this big semicircle, and therefore each of them is equals to 2. So I'll write it down. PD equals to 2, and PS also equals to 2. Likewise, QS equals to QC. Both those two line segments are the radii of this small semicircle, and therefore each of them is equals to 1. And we have here line segment CF. The length of line segment CF is unknown, so we define the length of this line segment CF as x. So here we have the radius PL of this big semicircle. The radius PL that is equal to 2 is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, you can implement rule 1. So I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. In addition, we have also the radius OM that is equal to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius PL of this big semicircle that is drawn to point L, that is the point of tendency of tangent AE with this big circle, and big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If A is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius GQ of this small semicircle that is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. According to the same rule that said that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. So I'll write it down. In the next step, we will prove that the big right triangle LPF is similar to this small right triangle GQF. So I write it down. We prove that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PLF. In the big right triangle LPF. And it is equal to this angle. That is actually angle QGF. In the small right triangle FGQ. So I'll repeat again. We actually found out that angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle GQF. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it is belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to angle alpha as it is belongs to the small right triangle GQF, it will be defined as angle GFQ. So repeat again, I can find out that this equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle LPF. In the big right triangle LFP, and it is equal to this angle, that is actually angle GQF. In the small right triangle GFQ. So repeat again. Angle LPF in the big right triangle LFP equals to angle GQF in the small right triangle FGQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the figures inside the big right triangle LPF are correspondingly equal to all the figures inside the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle LPF is similar, this is the sign of similar to the small right triangle GQF according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We derive the side LP in the big right angle LPF over side GQ in the small right angle GFQ equals to side PF in the big right angle LPF over side GF in the small right angle GFQ. So repeat again. We will derive the side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side GF in the small triangle. LP is the radius of the big semicircle that equals to 2 over GQ. GQ is the radius of this small semicircle that is equal to 1, and it is equals to PF. What is the length of PF? PF in total equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x. Over QF. QF in total equals to 1 plus x. So actually found out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And we get that 2 times 1 plus x equals to 4 plus x. Here we'll open the brackets of this side of the equation, and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. So here we subtract x from this equation, and you get that 2x minus x is x, so in total in this side of the equation we have x plus 2, that equals to 4. Here we subtract 2 from this equation, and finally get that x equals to 4 minus 2, that is 2. So actually found out that x equals to 2 units in its length. That is to say, side CF is equals to x according to our definition is equals to 2 units. So write it down. X equals to 2 units in its length. In the next step, we will prove that the big right triangle ADF is similar to this small right triangle ECF. So write it down. We will prove that the big right triangle ADF is similar to this small right triangle ECF. So why the big right triangle ADF is similar to this small right triangle ECF? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ADF. In the big right triangle ADF, and it is equal to this angle, that's actually angle ECF. In the small right triangle EFC. So repeat again, we found out that angle ADF in the big right triangle ADF equals to angle ECF in the small right triangle ECF. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to this angle alpha, as it is belongs to the small right angle EFC, it will be defined as angle EFC. So repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you read this is angle DAF, in the big right triangle AFD, and it is equals to this angle, that is actually angle CEF, the small right triangle EFC. So repeat again, we actually found out that angle DAF in the big right triangle AFD equals to angle CEF in the small right triangle ECF. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the triangles inside the big right triangle ADF are correspondingly equal to all the triangles inside this small right triangle ECF. And therefore those two triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle AFD is similar to the small right triangle ECF according to angle similarity rule. And from the fact that the big right triangle ADF is similar to this small right triangle ECF, we will derive that the following relationship exists between their sides. We will derive that side AD in the big right triangle ADF over side EC in the small right triangle ECF equals to side DF in the big right triangle ADF over side CF in the small right triangle EFC. So repeat again. Actually found out that side AD, the big triangle, over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3 over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. In total, DF equals to 2 plus 2 plus 1 plus 1, that is in total 6. 6 plus 2 is 8. So in total, DF equals to 8 over CF. CF equals to 2. So in conclusion, we should find out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So I write it down. We should find out that 8 over 2 is 4. So in total, C over EC equals to 4. Here we multiply this equation by EC, and we get that 3 equals to 4 times EC. Here we divide this equation by 4, and finally get that the missing side EC equals to either 3/4 or 0.75 units. Okay, so I should find out that this is the missing side EC that is equals to either 3/4 or 0.75 units. So I write it down. EC is equals to 0.75 units. What is the length of this side BC of rectangle ABCD? We have the rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD equals to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So I write it down. We should find out that side BC equals to 3 units in its length. What is the length of this missing line segment? Line segment BE. From the drawing, it is very easy to see that BE equals to BC minus EC. Again, BE equals to BC minus EC. So I write it down. I should find out that BE equals to BC minus EC. So BE equals to BC. BC is 3 minus EC. EC is 0.75. So in total, BE equals to 3 minus 0.75 is actually 2.25. So this is the missing side, the missing line segment BE. This equals to 2.25 units in its length. What is the length of side AB of a rectangle ABCD? According to the same rule that says that the opposite sides of a rectangle are equal to each other, we will get that in rectangle ABCD, side AB must be equal to the opposite side DC. DC in total equals to 2 plus 2, that is 4, plus 1, that is 2, and 4 plus 2 is 6. So in total DC equals to 6, and therefore the opposite side AB must be also equals to 6 units in its length. In the next step, I'll copy the green right triangle ABE in a new page, and we will implement the Pythagoras theorem in this green right triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side AB equals to 6 units in its length. Side B equals to 2.25 units. And the hypotenuse AE is the missing side. Here by PT is the relation for Pythagoras theorem. So actually, this is the right green triangle ABE that they call from the original drawing. According to the Pythagoras theorem, this right triangle ABE, AE square equals to AB square plus BE square. So I write it down. AE square, that is the square of the hypotenuse, equals to AB square plus BE square. AE is the missing side, so we leave it as it is. AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 square. That is equals to 5.0625. So in total, AE square equals to 36 plus 5.0625, that is actually equals to 41.0625. Here we take a root out of this equation, and finally we get the missing line segment AE, that is actually also the hypotenuse of this right triangle ABE. It is equals to the square root of 41.0625. That is actually equals to 6.408 units. And that is the answer to the question. Okay, again, actually found out that the length of this line segment AE is equals to 6.408 units. Okay, so in the next step, I'll summarize the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing, we have rectangle ABCD. We know that side AD equals to 3 units in its length. In addition, inside this rectangle, we have those two semicircles. The radius of the big semicircle, this big semicircle is 2. The radius of this small semicircle is 1. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside the rectangle are right angles. So those 4 angles are all right angles. In the next step, we define the relevant points to this question with letters. We define the center of this big semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. We define the touching point of those two semicircles, this point is point S. Likewise, we define the point of tendency of tangent AE with this big semicircle, this point is point L. And finally, we define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did the construction. That is to say, we extended side A, line segment AE and side DC of this rectangle by a straight line until they touch each other. This is their touching point. We define this touching point as F. So, actually, we extended side DC of rectangle ABCD by a straight line. First of all, DC is one side of a rectangle, it is absolutely a straight line. Then we extended the straight line DC by a straight line, and the result is DF. When you extend the straight line by a straight line, the result must be a straight line. So DF is a straight line. If you focus on the upper side of the straight line DF at point C here, the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is the right angle, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the right triangle ECF, we define this angle EFC as alpha. So, in this right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees, that is the sum of the angles in the triangle. Likewise, in the big right triangle EDF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the rule that says that the sum of the angles in the triangle is equal to 180 degrees. Here we have PD equals to PS, the above the radii of this big semicircle is equals to 2, so each of this line segment is equals to 2. Likewise, we have QS equals to QC equals to 1. the above area of this small semicircle that is equal to 1. Here CF, we find the length of this line segment CF as x. So here we have the radius PL of this big semicircle that is equal to 2. The radius PL is known to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have radius that is known to the point of tendency, then tangent AE will be perpendicular to the radius LP. If A is perpendicular to LP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle that is known to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius that is known to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If A is perpendicular to GQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the sum rule, rule 1. So in the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. In the next step, we put that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha. This is a common angle that belongs to both angles. So we can write down that angle alpha equals to itself is a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the figures inside the big right triangle LPF are correspondingly equal to all the figures in the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle, similar to rule. We shall find out that the big right triangle LPF is similar to the small right triangle GQF according to angle, similar to rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP in the big right triangle LPF or side GQ in the small right triangle GQF equals to side PF in the big right triangle LPF over side QF in the small right triangle EFQ. Okay, again, we will derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side GF in the small triangle. LP equals to 1 over GQ equals, LP equals to 2 over GQ that equals to 1, and PF equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x over QF. QF in total equals to 1 plus x. So in total we shall find out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation, and finally found out that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtracted x from this equation, and finally found out that here we have 2x minus x is x, so in total on this side of the equation we have x plus 2. On the other side of the equation we left only with 4, so x plus 2 equals to 4. We subtracted 2 from this equation, and finally found out that x equals to 4 minus 2, that is 2. So we found out that the missing 9/7 CF is equals to x is equals to 2 units. In the next step we prove that the big right triangle ADF is similar to this small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the angles in the big right triangle ADF are correspondingly equal to all the figures in the small right triangle ECF, and therefore those two right triangles are similar to each other according to angle, similar to rule. So repeat again, I shall find out that the big right triangle ADF is similar to the small right triangle ECF according to angle similar to. And from the fact that the big right triangle ADF is similar to the small right triangle ECF, we derive that the following relationship exists between their sides. We will derive the side AD, the big triangle, or side EC, the small triangle, equals to side DF in the big triangle, or side CF in the small triangle. Repeat again. We will derive that side AD, the big right triangle ADF, or side EC, the small right triangle ECF, equals to side DF in the big right triangle ADF, or side CF in the small right triangle ECF. Okay, AD is 3 over EC. EC is the missing side, so we will leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is in total 6, plus 2 is 8. So in total DF equals to 8 over CF. CF is 2. So in conclusion, we can find out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So in total we can find out that 3 over EC equals to 4. Here we multiply this equation by EC and finally found out that 3 equals to 4 times EC. Here we divided this equation by 4 and finally found out that the missing side EC equals to either 3/4 or 0.75 units. Repeat again, we found out that this missing side EC equals to either 3/4 or 0.75 units in its length. So what is the length of the missing side BC of a rectangle ABCD? According to the rule that said that the opposite sides of a rectangle are equal to each other, in rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3. So what is the length of the missing 97 BE? BE equals to BC minus CC. Again, BE equals to BC minus CC. So BE equals to BC, that is 3, minus EC, that is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. So BE equals to 2.25 units in its length. What is the length of the missing side AB of rectangle ABCD? According to the symbol that says that the opposite sides of a rectangle are equal to each other, so in rectangle ABCD, the opposite sides are equal to each other. That is to say, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC in total equals to 6, and therefore the opposite side AB must be also equal to 6. So AB also equals to 6. In the next step, I copied the right green triangle ABE in the new page and implemented the Pythagoras theorem on this green right triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the square from the perpendiculars. So this is the right triangle ABE that I copied from the original drawing. So in this right triangle ABE, AE square equals to AB square plus BE square. AE is the missing side, so we leave it as it is, and it equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 5.0625. So in total, AE square equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So in total, we shall find out that AE square equals to 41.0625. Here we took out of this equation and finally found out that the missing 97 AE, that is also the hypotenuse AE, is equals to the score to 41.0625, that is actually equals to 6.480 units. Repeat again, we shall find out that the length of this 97 AE is equals to 6.408 units. Okay, thank you very much.